This standard is broken into three parts, and we will take them one at a time. The first one is to explain why the slope m is the same between any two distinct points on a non-vertical line in the coordinate plane. The standard asks us to do this using similar triangles, and the reason we're doing this is because the similar triangles ties us together with things that we've learned from geometry. And if you remember, all of mathematics was initially created in the geometric world before coordinate planes, before algebraic symbols, and the beauty of mathematics is that it all ties together. So we're going to take things that we know from geometry and apply those now to what we usually consider as algebra. So let's begin with 2 points, P and R, in the coordinate plane somewhere, and we're going to assign names to their coordinates rather than giving them specific coordinates. So the names we'll give them is Px will be the x-coordinate of P, and P subscript y will be the y-coordinate of the point P. And likewise, Rx and Ry represent the horizontal and vertical components of the point R as well. Now these 2 points, because they're not, one is not above the other, we can agree that Rx is not going to be equal to Px. Otherwise we'd have a vertical line, and we're not looking at vertical lines. So they'll create a line, and we'll call it L. This line L is the name of our line. And our first job is to explain something about the slope of this line. And we'll get that slope by drawing a horizontal line from P and a vertical line from R, which intersect at a point Q, and we've created a right triangle. That is, we sometimes call our slope triangle. Now Q, if you think about its coordinates, the x-coordinate of Q is the same as the x-coordinate of R, and the y-coordinate of Q is the same as the y-coordinate of P. So Q has coordinates Rx and Py. Now what we want to do is figure out what the slope is for this line. And as you recall, the slope is generated by the ratio of this vertical, the length of the vertical to the length of the horizontal segment of the slope triangle. So this is the horizontal distance, PQ, we'll call it the length of PQ. And I'd like to explain exactly what that is in terms of these coordinates. So if you remember, this distance here is given as Rx. From here out to here, that's the x-coordinate of the R point, and the x-coordinate of the P point, Px, takes us to here. So if we want to know what the length is PQ, then what we need to do is take Rx, and if we subtract off Px, this Rx plus minus Px, that's what's left over to give us the length of PQ. So from a coordinate point of view, PQ is equal to Rx minus Px, Rx minus Px. And in a very similar fashion, we can see that Rq is Ry minus Py, this Ry minus Py. And so the slope, which is given here, the slope of this line is given by the length of Rq over the length of PQ, which is Ry minus Py over Rx minus Px, and that's the slope m. Now we've shown this in one form. It's the ratio of two lengths. Here's how we calculate the lengths by subtracting coordinate pairs, and you may have seen this as y2 minus y1 over x2 minus x1. That's a common way to see it, but that's how we can calculate the slope given any 2 points, and it's given m, given it by the letter m. We use that letter m, which is comes from the French word for mountain, montagne. Other ways of thinking about slope are a change in y over a change in x. This triangle here is the Greek